Hi, it's time for another math easy solution. Turn to discuss further into the discovery project rotating on a slant video series and go over question 4. Basically, recap, the discovery projects are at the end of each chapter of my calculus book. Are some pretty interesting mathematical projects for a slightly more advanced math. And in this case, we are dealing with rotating on a slant. So if we have a region like this rotated about here, and this series involves finding like areas, for example, about between this curve and this line, as well as finding the volumes formed when you rotate it about here. Volume, and then later we'll do surface area. Yeah, and now just to recap on the previous questions. Question 1, I showed the area of this region right here for a general, basically general function, and then this is a general line y equals mx plus b, slanted line, and I show that it equals to this. So again, make sure to watch those earlier videos. So question 2, I use an example where we had a specific function, specific line, using that formula. In question 3, I showed the volume when you rotate that shape about the slanted line, and I showed that for a general function, it's this. And now for question 4, we're going to use this part 3, but for a specific example, which is the same one right here for question 2. And question 4 just states, find the volume of the solid obtained by rotating the region of question 2 about the line. About the line y equals x minus 2. So that's this region right here. So if I were to just to copy and paste it about here, just to show you what I mean. So when we rotate this, we get a volume. So rotate this symmetrically across like that. Let's draw this better. And then this goes to here, something like this. And then draw 3D. So when we rotate this shape, we get something that looks like, let me just draw it bigger, or just a bit more accurate. So we get a shape like this, and we get a volume. So this is just in 3D, imagine that. So we have this volume right there, and we're trying to find volume V. So this volume, we could again just use this formula that I went over in my last video. I derived this, so we can use that. So we know that volume is equal to pi over 1 plus m squared power of 3 over 2. And I'm just rewriting this right here. So from P to Q, PQ, and then this is going to be f of x minus mx minus b. This is squared. And then we have 1 plus m times f prime of x dx. So let's look at this one right here. M is just a slope. So if we look at that general function, yeah, M is just a slope, B is the other part of the line, Y is f of x, that's P and Q. So in our case, for this specific example, if we look at this, let's just find all the variables. So at this 0, this point is just our P. So P is equal to 0. Now this all the way down here, if I were to go all the way down, this is 2 pi, so that is our Q. And now this y equals x minus 2 equals to, well, just mx plus b. So our m is equal to the slope of this line, which is just 1. And our b is equal to, well, negative 2. So negative 2, so we have everything there. And our f of x is equal to, that's just y equals x plus sine x. So x plus sine x, and then the next part we need to find out the derivative. So f prime of x is just equal to derivative of this. Derivative of x is 1 plus sine, derivative of sine is just cos of x. So putting this all together, we get volume, or V, is equal to 1 plus, this is going to be 1 plus 1 power of 3 over 2, which is just 2 to the power of 3 over 2. So that's just 1 plus 1 is 2. 1 squared is just 1. Integral now, so from P to Q, which is 0 to 2 pi. 0 to 2 pi. So now we put the f of x, which is just our, which is going to be our x plus sine of x minus now m, which is 1, so minus x, and then minus b, which is minus 2, so that's plus 2 squared. And now we have this 1 plus m. Again, m is 1, so 1 plus m times f prime, which is going to be 1 plus cos x dx, like that. So a couple things to just try to simplify this. This 2 over 3 over 2, 2 over 3 over 2 is equal to, this is the same way as writing it as equaling 2 to the power of 3 and then 1 half, power 1 half. This equals 8. 2 cubed is 2 times 2 is 4, times 2 is 8. So this is 8, 1 half. You could just write this as square root 8. And then this, simplifying this next step, we get v is equal to, so this is square root 8 times by 0 to 2 pi. The x's cancel. We're just left with sine x plus 2 squared, and then this 2's add up. So cos x plus 2 dx. So now what we're going to do is FOIL this all out. I'll just simplify it by writing this integrand by itself. So cos x, sine x, so sine x plus 2 squared times cos x plus 2. First what we'll do is expand this squared brackets right here. So sine x times itself, we're going to have sine x squared, sine x times 2. Do that twice when you FOIL this out. Then those add up, we'll just get 4, or 2 times sine x. So 4 sine x, 2 times 2 is going to be 4. Multiply this all by cosine x plus 2. And now we're going to FOIL out further, so multiply cosine of x by 4, by this, and by this. Write this a bit better drawing. And then add it up to 2 times 4, like that. So we're just going to FOIL. So this equals to further cosine of x, so sine squared of x times cosine x. And then we have 4 sine x cos x. Now we have 4 times cos x. And then plus 2 times sine squared plus 8 sine of x. Then plus 4 times 2 is 8. So now that we've FOILed it out to something like this, what we're going to do is just put all the ones that are difficult to integrate by themselves, and put the ones that you can integrate fairly easily together. So this one, this 8 sine of x and 8, those are pretty straightforward to solve. So what I'm going to do is write this out as just the volume, because remember this FOILed out is just this inside integrand bracket. So these two brackets all FOILed out. So our volume is equal to pi over square root 8, and now what I'm going to do is break this up into a bunch of integrals. So from 0 to 2 pi of this first one, sine squared of x cos of x, plus 4, this is 0 to pi, that's this part, sine x, I'll write this 1, this 2, and then this is going to be our 3, and then this other one, I'll combine it together for the fourth one. So we get sine x cos x. It's just to make it easier to solve. And then plus the third one, put this one first, 2 sine squared of x, 0 to 2 pi, and then plus this next one, but there's a common factor of 4, so I'm going to take the 4 out. Take the 4 out, 0 to 2 pi, and now we have this bracket like this. This is going to be the 4 has been taken out, so cos of x plus 2 sine of x, then plus 8 divided by 4 is just 2 dx. So we have basically 4 integrals right here. So again, I'll write this 1, 2, 3, and again this is all multiplied, every single one by pi over square root of 8. And 4. So I'll solve these all step by step so it's easier to digest. So the first one, we'll do this number 1, which is integral from 0 to pi of sine squared of x cos x dx. And again, this is similar to before. I showed in, I think it was question 3 or question 2, one of them, where we could just use substitution because, so use substitution because we know the derivative of sine of x is just cosine of x. So in this case we let, so if we let u equals to sine, sine of x, then the du is just equal to, well, cosine of x dx, which is exactly this, so we could just replace it fully. So now what we also know is at x equals to 0, we have u is equal to sine of 0, which equals to 0. And again, to recap on that sine curve, if you just look at it, x, y, sine curve looks something like this, which is basically this, this is 0, this is y equals sine of x. And also at this point right here, which is 2 pi, it's also 0. And we'll get that here, which is at x equals to 2 pi. We have u is equal to this interesting sine of, well, this is sine of x, so sine 2 pi, which also equals to 0. So this has no area because the intervals are the same, just 0. So what we get is this 0 to 2 pi of sine squared x, this is cosine x dx, is equal to, when you change the variables, integral from 0 to 0 of this is going to be u squared, and then cosine of x dx is equal to du, which is just 0. We don't even need to evaluate it because integrals are from 0 to 0, so it has no area or no net area across. And again, you can learn more about this in my earlier videos on integration and their properties. So now that we have that 0, let's go back up. So this whole integral is equal to 0. Let's look at number 2, which is 4 times, so number 2, we have 4, integral from 0 to 2, and it goes as sine x cos x. So sine x cos x dx. Now this one, we could just use the trig identity. So if we recall the trig identity, which I covered in my earlier video links in the description below for that. So recall, let's write trig identity. So if we recall these trig identity, which is sine 2 of x, is just equal to 2 sine of x cos of x. So in our case here, we have 4 sine of x cos of x, so we can get now, so we get 4 0 to pi sine of x cos of x dx is equal to, well, this is equal to just 2 times sine 2 of x, because we have a 2 sine of x cos x times by 2. 0 to pi, this is going to be sine 2 of x dx. And we can evaluate this integral fairly easily. The integral of this is just 2, and this is going to be, well, this is going to be cos 2 of x, but negative because cosine of x, derivative of that is negative sine of x, so we have to do the negative, and chain rule we have to divide by 2, so that this derivative becomes sine 2 of x, because if to do is chain rule multiplied by 2, it cancels out. So that's what that integral is, from 0 to 2 pi. Then these 2's is a constant, we just cancel that out. So we can just ignore that. So now plug in this, we get negative cosine, let's remove this cosine, put the 2 pi in there, we have 4 pi. Yes, a 4 pi minus, and now we have, plug in this 0, minus negative cosine 0. Yeah, because 2 times 0 is 0. So we have this right here, and again, recall that the cosine curve, how it looks like. So if we draw this out, this is x, y. The cosine curve is just periodic like this. It keeps going on and on. This is y equals, this is just the positive side, cosine of x. So at 0 we have 1, and these peaks are 1. It keeps going on, and at this point right here, this is 2 pi, and again it repeats itself, keeps repeating itself. This is 4 pi. and it goes down and up, etc. This graph doesn't look too good, but again, you get the point. So this point is 1, this is 1, so this equals 2, negative 1 minus, well, minus and then plus 1 right here. This just cancels again. So it equals 0. So we have, yeah, this is going to be negative 1. When you minus a negative 1, it becomes positive right here. So we get 0 again. Let's just go back here. So this equals to 0. So we have two integrals equal to 0. Now look at the third one, which is 2 sine squared of x. So the third one, which is 2 sine squared 0 to 2 pi of sine squared of x dx. Now this integral, I've solved this in my earlier video before, and in that video I used that basically trig identity, basically recall trig identity. We could write this in terms of cosine, because we want to get rid of this squared value, which is just messes things up. So recall the trig identity, which is just cosine 2 of x is equal to 1 minus 2 sine squared of x, like that. So we have this trig identity, so now we can just rearrange this. We get sine squared of x, move this on itself, subtract this out, divide by 2. This equals 2, 1 minus cosine 2 of x, all divided by 2. So if we just recall this one, again I proved this in my earlier video, look at the video description below for this trig identity. So now what we get is 2, 0 to pi of sine squared of x dx equal 2. These 2's cancel, there's a bottom 2 in this 2. So we get 0 to 2 pi of 1 minus cos 2 of x d of x. Yeah, dx. This equals 2, just evaluate it. Integral of 1 is just x, minus integral of cosine 2 of x is just sine 2 of x, divided by 2. This is the chain rule. So this is from 0 to 2 pi. So this equals to 2 pi minus sine of 4 pi divided by 2. And then minus, this is going to be 0 minus sine 0 over 2, and again I showed sine 0 is just 0, and then sine 4 pi, let's just go back up to that curve. This one, it's symmetric, I mean it's periodic, it keeps going on, and then it goes to 0 as well at this point, which is going to be 4 pi. So it's just periodic about 2 pi. So that's also 0. So this goes to 0. So all we're left with is just 2 pi. So it goes 2 pi. So put this back up here. Where's the overall integral? So this 3 is equal to 2 pi. And now this last one here, which is 4, integral from 0 to 2 pi of cos x, 2 sine of x plus 2. So let's just go scroll here. So the fourth one is just going to be, I think it was 4, 0 to pi, and then we have, what was that, cos of x? Yeah, cos of x plus 2 sine of x, and then this was plus 2 dx. Let's write this neater, cos of x. So we get something that looks like this. And this one's easy, we can just integrate these each separately. So this equals to 4, integral of cos of x is just sine of x. And then plus integral of sine of x is just negative cos of x. So 2 cos of x. And then plus 2x. 0 to 2 pi. This just equals 2, 4. Then plug this in, sine of 2 pi minus 2 cosine 2 pi plus, this is going to be 4 pi, and then minus, I'll put this in bracket like that, minus, put in the zeros, sine 0 minus 2 cos 0 plus, well, 0, 2x, 2 0 is just 0. So we get something that looks like this right here. And now let's just try to evaluate it. Sine 2 pi, again I showed this is just 0. Cos 2 pi is equal to 1. So this part right here is equal to 1. And 4 pi, the sine of 0, again that's 0. And cos 0 is equal to 1. That's just 0 right there. So this equals to 4 times it by, we get inside here, this is going to be, let's write this, we don't need the brackets there, negative 2 plus 4 pi, so negative 2 times 1, and then we minus, right here, this is going to be minus negative 2 times 1, which is just negative 2, and all the zeros are there. So we get this equals to 4 times negative 2 plus 4 pi plus 2. So now these 2's just cancel. So we're equal to 4 times 4 pi, which equals to 16 pi. So that's 16 pi. Let's just scroll all the way back up. Put that inside our integral. This equals to 16 pi. So the integral is going to be pi divided by square root 8 times it by 2 pi plus 16 pi. So that is our, basically we got our answer now. Let's just, so thus volume is equal to pi over square root 8 times it by 2 pi, because everything else is 0, plus 16 pi. Let's put this in regular brackets. So you could write the answer as 18 pi over square root of 8, this is pi squared. So pi squared, and there is our answer, except you could write this simplified further. My calculus book kind of writes it as, well, the square root 8. You could write this one as square root 4 times 2, which is just square root 4 times square root 2. Square root 4 is just 2. So you could write this as volume, doesn't matter how you write, these are all the same answers. 18, you could write this as equal to pi squared divided by, this is going to be 2 square root 2. Well, let's write this as, here I'll write it for completeness, this equals 2, 9 times 2, 18 is 9 times 2, whoops, pi squared over 2 square root 2, the 2's cancel, so again you could write this as pi squared over square root 2. Or what you could also do, again, my calculus book, I don't know why it writes it differently. It writes it as the answer. Let's go simplify this further. Times square root 2 over square root 2. It doesn't like using square roots at the bottom. So you could write this as, this is going to be, this cancels, this will be 2. So it'll be 9 times square root 2 pi squared over 2. So this is the answer my calculus book has. But these are all the same, and if you're doing an exam or whatnot, it's all going to be exactly the same answer. You're going to get full marks. Anyways, that's all for today. If you learn from this pretty extensive example on solving this example, I'm solving a specific example on a shape rotated by a slanted line. And again, this shows you why this is on the discovery project as opposed to just general questions in my calculus book, because it's a bit more advanced, well, in terms of just more tedious in solving any generic shape rotated by a slanted line. That's why we never deal with one too often in just calculus class. We never did deal with vertical or horizontal lines, because it's much with less time consumption, or conducive, and less time conducive to finishing. Anyways, that's all for today. If you learned this pretty extensive example, make sure to watch my other questions, as this is a very interesting discovery project. Anyways, thanks for watching, and like always, you can download these exact notes in the link below, and stay tuned for another Math Easy.